With that said, why don't we move on? I want to show you some things that you're going to get wrong. You're just simply going to get wrong when you start writing asynchronous code. And when I say wrong, I don't mean errors like you're going to fail to call a task. You're not going to await it. You're going to get that nasty error message saying, oh, failed to await something. I mean, you're going to defeat the entire purpose of doing this in the first place. Let's take a look. Here's the story. Let's say we have a database. And in that database, we need to do a bunch of queries. And the database is remote. And each one of the queries is actually fairly expensive to run. But all of the computation is being done remote, not on our local end. Our program is just asking the database to go do some work and then give us the results. And so if we were to write this serially, well, we're going to be spending a lot of time waiting for the database to get back to us that we otherwise are completely idle. So we're going to say to ourselves, let's make this asynchronous. Let's say that when we shoot off a database request, and that database request is churning in the database, it's doing all of the data loading it needs to do and all the data manipulation it needs to do, we're going to allow ourselves to go and run some other code. So we'll set ourselves up wanting to run a couple of queries. And the simplest queries that we can run are just a couple of select statements that just select individual values, something like that. So here are our queries. And what we want to do is we want to shoot those off to our database. Well, how do we structure this? Well, as a consequence of async I/O being fundamentally single-threaded within a single process, we can share state pretty readily within different units of computation. So a very simple way for us to get started would be, let's write our entry point. And let's go through each query. And we'll dispatch each one of those queries to maybe our database connection, like this. We'll await executing the query, and that's our result. And we'll just print out the result. Like that. We'll pull in our import for AIO SQLite 3, AIO SQLite, without the 3. And we'll enter this entry point with our run. This is async IO, like that. And then here, we'll just fix a small typo. And there we go. You can see those are the, and let's actually strip this. Let's not run the ones that are empty. And let's also dedent this, just so that we have something that is nicely indented. So there we go. We have our 4 queries. And that seems to be pretty good. I guess we might want to share the database connection. We don't want to spend the cost of setting up that database connection over and over, so that seems pretty good. Except we've kind of defeated the purpose of using async IO in the first place. This is fundamentally blocking. We're basically going to run each query, and we're going to await each query. And when that query is done, we're going to go to the next query. And when that next query is done, we're going to go to the next query. And when that query is done, we're going to go to the next query. Why did I bother with async IO in the first place? This could have just been done with a regular old synchronous SQLite. I gained nothing. One of the major things that is going to get in our way when we write async IO is failing to realize that we have basically written serial code that blocks anyway, that is no different than just the regular old non-async IO code. One of the ways you might think about that is if your program has no use of gather or task groups or anything similar, it's very likely that you might have many units of computation that are just blocking on each other, and you're not really gaining anything from using async IO. What I'm missing here is I probably want to first set up the problem that I want to solve. For example, set up each one of my queries. So I can do something like this. And I can do this just a regular list comprehension. Remember that even though this thing here, this con.execute is something that I await, it's an asynchronous task, fundamentally, it looks like this. It's really just a function that returns a unit that gets awaited. And so I can use just the most basic Python, just the absolute most basic Python structures. I could even do something like this. I could say map this to each one of the result values like that. And then I can gather these. And it is really the gather that is the key to what I want to do effectively here. I can gather my queries, and that gets my results. And for my results, I could do something like this. Could loop through them. And I could say queries. Here we could take our query and our results. We'll zip them together. And here what we'll do is we'll say queries of this equals result. And we'll group them together. So when we're done here, we should see each query and its resulting value. Now, of course, there's one more thing we have to do. Here, this needs to be moved down here to make use of that. And then finally, the resulting value here, this needs to actually be awaited. And that needs to be unpacked. So here we have to unpack that like that. And then finally, let's check one thing that we did wrong here. That's zipping the queries. That's each individual query. That's good. So let's turn some of these pieces off and just take a look at what we have. Really interesting. So let's just check what this is giving us. Oh, and that needs to be unpacked like that. There we go. So there we go. You can see the error handling is not that ideal. We get a lot of issues here. And here we're going to await the cursor and then unpack the results. Now let's see what we get. Here we get each individual cursor. And then that needs to be looped over. So here we're going to do this. And here I think that doesn't need to be awaited because the async for will do that for us. So there you go. You get each one of these and the resulting value coming out of that. Now, there's a lot of mechanics here, but largely you can see that we can reason our way through how this all works. Fundamentally, we want to asynchronously create a database connection because it's going to maybe do some things behind the scenes, and maybe for creating multiple database connections, like if we want to lift this up, we want to do queries from database with the source. And if you don't supply the source, it just uses the in-memory database, like that. And then here, we do this at a higher level as well. And then if we wanted to do something like this, and here we'll pass in the queries as well. And we wanted to gather queries from database, maybe multiple of these. And here we'll do this against our in-memory database with our queries like that and like that. And then here we go. And by the way, let's there we go. And then here this should be returned. There you go. You can see we've done this against multiple different data sources, and we've done that asynchronously with the actual connection to the database done asynchronously. Largely, that's why we have to do the async with here. Here, we didn't have to do anything special. We're just creating the tasks. Gather requires that we go off and we invoke that event loop, so we have to await that. Zipping them together, we don't have to do anything special here. This is just the results of that plus something else. And then here, this is something small, a little bit detailed, and it's related to how AI SQLite works. Specifically, the cursor that you get back doesn't load all of the data. It allows you to asynchronously fetch that data. This is why we need an async for in this asynchronous comprehension syntax. The other major thing that we might fail to do in our asynchronous programs, other than failing to actually make use of the asynchronous behavior, is we might inadvertently block. And this comes up quite a bit. And this is where things start to get a little bit tricky. If it were the case that I had my asynchronous main, and this calls some asynchronous task called task, And here we'll launch into this from our entry point. And this task calls some other task. And then all the way down the line, this calls just a regular time.sleep. Well, we just lost all of the advantage of async IO in this. Here, this should be run with this one little detail. It's very easy for synchronous code that blocks to find its way into our program without us paying attention if we're trying to take some existing program and swap it over to async IO. And here, the consequence of this is because this didn't tell our scheduler, oh, I'm waiting for the sleep to come back, you can go and do anything else. It'll block this task, which will block this, which will block all the way up, and it doesn't matter if we're gathering 10 of these. We have probably now just implicitly serialized everything. Generally, when we're writing async IO code, we need every unit all the way down to the deepest level to basically be async aware. And we need support in the deepest of our libraries. Anything that interacts with C code needs to have support. Now, that might seem clumsy, and in fact, if we're trying to backport an existing program to use async IO, it can be very clumsy. If we're writing our code from scratch, we can be a little bit more diligent. But in other programming languages which seem to avoid this, largely what they're doing is they already have implemented that support at the core levels, and they just happen to be languages which don't hook out into into C code as often. You can think that in Python, we are so ready to hook into C code in tools like pandas and NumPy. Well, we're going to hit some C barrier that's just going to block everything, and it's quite easy for us to end up getting ourselves blocked. And so our conclusion here is really make sure that you are doing work concurrently, avoid implicit serialization, make sure you are using, say, gather or a task group. The second thing is really make sure that all levels of your program support async IO, all the way down to the core library levels. So one thing that you might think is, if it were the case that you're reading from a file with open, who knows where that file is located? What if it's locating an old spinning Rust media? That could be a blocking operation. It could block your entire program. Well, if that's the case, you might actually need a third-party library like AAO files. And you may need to asynchronously open that connection just to make sure that you're not blocking there. And you can think anytime you interact with the outside world, there's always some risk of you calling a system call that could block. You may need support all the way down. For languages that unify this a little bit better than Python, where they have one unified event loop, understand that there are still system calls that you may need to run. You still need deep support for this, all the way down to the deepest levels that you have. Otherwise, some system call, some innocuous system call like a stat that you call, blocks everything, and you just lost all the benefit of using async IO in the first place. Setting that aside, I want to talk about some specific mechanics of async IO. I mentioned a couple of times gather as well as task group. I want to show you what task groups are, because there's something that is relatively new in async IO. The first versions of async IO in the standard library did not include task groups. It's an idea that you may have come across if you use tools like Curio or Trio. You may have heard these called things like nurseries. Let's take a look. Here's the nature of one of the problems that we might have when we work with async IO. Well, one of the advantages of async IO is that we know when things will run and when things will be interleaved. In other words, if I have some shared data, and that shared data is a dictionary, and I have two tasks, task 1 and task 2. And both of these operate with that shared data. So maybe what this does is this takes the size of the shared data and it does some operation here, maybe just store something random to this thing. And this does the same thing. You can think this read from the data set and then write back to the data set in a threading scenario could be very risky because you don't control when you're interleaved. So you could be interleaved when you did the read, but before you did the write. Somebody else can interleave in some way that this results in garbage data. Well, with the global interpreter lock, that still can happen because a global interpreter lock only guarantees that one bytecode runs at a time, not that one line of code runs at a time. This one line of code consists of multiple different bytecodes. So even with the global interpreter lock, we still have to have locking. But in the asynchronous universe, we don't have to worry about that at all, because no matter how we write this, the only places where we can be interleaved are the places where we specifically designate you are allowed to come in and do some work while I'm waiting for something else. Places where you see that await keyword. And so here, we might await here a sleep of 0 is our basic way to say, you know what, let somebody else do something. I actually will sleep for 0 seconds, come right back if there's nobody else doing any work, but otherwise I'll let somebody else do some work. So our AIO sleep 0 is basically our notion of saying, you know what, you go do something. I'll just take a micro nap here. Well, even though it's the case that this code is deterministic and we can understand it by just looking at what those interleaving points are, and we don't have to worry about, oh, is this going to run here? Is this going to run there? We can see exactly which blocks of code run atomically. It is the case that there may be some situations where we might see things kind of escape our understanding of how things run. Let me show you a simple example. Let's say we have a context manager. And let's make this actually just a regular synchronous context manager. And then we'll talk later about the asynchronous context manager. So let's start by launching ourselves into our event loop. Let's do something with just a regular context manager here. Like, for example, an open file. And we'll just open the same file as F. In this block, let's do something with that file. Maybe we'll call some task that makes use of that open file. And what we might do is we might say for each line in the file, we'll connect to a database. And here we'll just do an in-memory database, and we'll insert into that database. So here we could say, you know, create con.execute, create table contents, and here this just could be, you know, each line of the file. There we go. And then we could say something like, and we can move this a little bit deeper so we don't have to continuously recreate this connection. We might say insert into contents, the line. And then here, in the absence of knowing off the top of our head what our prepared statement syntax is, we'll do this in a very dangerous way. We'll do it like this, with just string concatenation, or with just string interpolation, and then we'll await that. So here, and then maybe at the end we can do something like this, con.execute, select star from contents, and then here this gets us a cursor, and then we can say for row, async for row and cursor, and print out the row. There we go. Now, let's fix our small syntax error. That should be good. Our syntax error is here. That's fine. And this should be insert into contents. Very good. Here we don't need that. And then finally, let's just print this out very quickly. Yeah, and the problem, of course, is in the absence of our stored procedure. Here, I think maybe we just pass this as, see if that works. Yeah, there we go. So here you can use the question mark syntax. So here you can see we inserted that. Now, for the most part, it seems to work. Huh. But there's a hidden flaw in all of this, and there's a slight mistake in all of this. Let's say that we say, you know what, the opening of that file, I'm not that comfortable with the opening of that file So what I'm going to do is actually, we can keep that as synchronous. What I'm going to do is I'm going to gather these tasks. And let's check one thing here. We're going to just do one small change to this. We're going to, let's try this. Here, we'll open that asynchronously, and then we'll read from that. Okay, very good. And then here we'll asynchronously go through that. Very good. And everything is fine. Well, in general, what happens when we have, say, a context manager is inside the body of that context manager, we can create these tasks. If we await these tasks and we block on this, then the only way for us to leave this context manager is once the task is completed. But if there's any possible way for us to escape this context manager with this task incompleted, for example, we do something like this, then we run into problems. Now, we've seen this before. It's constantly the case where if, for example, we have a context manager with an open file and we do a generator expression in that and we don't consume from that generator expression until we've left that context, we get the same error IO operation on a closed file. Here what we can see is we can guarantee in this particular case that this code is correct because we'll only ever leave this block once all of this code is complete. But if there happen to be multiple operations and they're not structured in a context manager, so for example, we did some setup operation like this and some other teardown operations and they weren't structured as a context manager, then the order in which these might actually execute might not be something that we can control, and we're not guaranteed that once we leave this block, everything has actually finished running. The asynchronous task group is an attempt to give us an easier ability to reason about blocks of asynchronous code. That is, to allow us to create a block of code. Inside that block of code, guarantee that everything completes before that block of code finishes. And if one of these errors outs inside that block of code, all of them get canceled. Let me show you what it looks like. If we import task group from asyncio, and we create an asynchronous task group here. In this task group, we can create tasks. So here, let's do this. And here we'll create 2 of them. And this should be create task. This is our other primitive for starting multiple different tasks that can run in, I shouldn't say in parallel because they can't strictly run in parallel, but they can run concurrently. Here, these 2 tasks, here we'll print this out. These 2 tasks will run in whatever order, and if we put a random sleep in here, like that, you'll see that, and we'll give these names. So this is task AAA, and this is task BBB, like that. You'll see that the ordering here is sometimes one first, the other next, sometimes reversed. What we're guaranteed with the task group is that all of the tasks will run, and they'll run to completion before we leave this one block. But we're not blocked on actually having to manually await them. Because you can think that if we wanted to do this in 2 different separate tasks, we'd have to either block on them, which means we've implicitly serialized everything. Oops, we got no benefit out of async IO. Or we might have to gather them like that. But there's a risk that what we might see is that one of these escapes that block and we have an operation on a closed file. With the task group, we're guaranteed that the only way for us to leave this asynchronous block is for everything to be completed. What you can think behind the scenes the task group is really doing is in the exit method or the aexit method, it's just waiting for everything to complete. This is not too dissimilar in your threading example from starting a bunch of threads in some thread pool and then joining on them. The core idea of the task group is that we can join on all of these, we can wait for all of these to complete. And if one of these happens to error out, let's do this, we'll have the first one error out. All of them are handled and canceled. Let's see if we can capture like that. There we go. So here, task AAA, and in some cases we should expect seeing just task BBB, but what you can see here is when task AAA is run first, it'll create this exception, which will then cause the entire task group to shut down and it'll cancel everything on its way back out. So our goal with the task group is to give ourselves a little bit more of an ability to reason about how things run, especially if things might be running in the background, they might escape our context manager. Now, where you see this actually happen in your real cases are, consider the following. Let's say that we have a background task that we want to run as part of, say, some fast API or Starlet system. We want to just constantly run in the background once the API launches. Well, what we have the ability to do in Starlet and fast API is, here this is starlet.applications, is we can specify a lifecycle. It's, I think, lifespan. And this can be an asynchronous context manager. So here, let's do it like this from context lib. Let's pull in an async context manager. And inside this, here if we can spell that right. And inside the body of this, we can create a task group and we can start some tasks. Note that here, if this has some access to some resource, and in the body of this, we are starting something that runs in the background, it's going to run within this context here. Well, we want, for example, if this context manager closes, for everything to be canceled and for everything to be closed. If you close, the task group, you close everything. And so where this will actually come up is, if we want to have some long-running background task in a Starlet or Fast API app, we may actually need to use a task group here. We do something like create a task group, and then here we create each task for each long-running task that we have. And here we can even cancel them, or we can let them be canceled as we leave this context manager. And if there's some context manager surrounding these, we can ensure that they all are able to, or they don't escape this context manager. They don't escape the context they're running in. So in conclusion, what we should see is when we have code that we want to run concurrently, we have basically two primitives in async.io. The first is async.io.gather, and the second is async.io task group. Task group is a little bit newer, and task group is a little bit easier for us to use because we can implicitly cancel things. With gather, what happens when one of them fails, all of them will fail. Although there's a flag on that, and we'll see that when we talk about accession groups. Task group gives us the ability to run some things in the background and to make sure that as long as we're running one of those tasks, we're within that context manager, there's no way for it to escape that context manager. There's no way for one of these tasks to run outside of that context.